Thanks, Robert. Got it. Very good. Well, welcome everyone to this evening's Immerse Australia presentation on this this cold winter, no, spring Perth night. Not that everyone's necessarily in Perth. That's where most of us are now tonight. Presenters and some of the organisers. My name's Andrew Woods. I'm a member of the steering committee of Immerse Australia. Immerse Australia is a national not-for-profit member organisation, association. Our goal is to support, promote and represent the immersive technology sector in Australia at all levels, from startups, freelancers and students to large studios, hardware and software providers and educational institutions. Our industry includes virtual reality, augmented reality, 360 video and immersive storytelling. If you're not already a member, I'd encourage you to do so. You can do that at the Immerse Australia website, immerseaustralia.org, and also follow us. You can also follow us on LinkedIn and Facebook for various updates. We're now organising a continuous stream of activities, whether they're online or face-to-face. Most of the face-to-face ones will be in Perth, because that's where most of the members are so far. Just a few housekeeping items first. We will hold all the questions until after the presentation, and there will be a good chance for doing that. You can either just hold your questions until then, or you can enter them in the chat function as we go along. You can feel free to have your camera on, but make sure your microphone's muted during the presentation. And just for your reference, the presentation is being recorded and will be available to Immerse Australia members after the event. So on behalf of Immerse Australia, it's my great pleasure to welcome our guest speaker tonight, Associate Professor Mihye Won. Mihye is with the School of Education at Curtin University. Her research at Curtin has involved investigating how to engage students in science learning in meaningful ways. She's currently leading 2 Australian Research Council discovery projects, one on exploring educational possibilities of immersive virtual reality, and the other on teaching for creativity in science classes. And tonight's presentation will be on the first topic that mentioned there. So without further ado, but I'll pass over to Mihye. Thank you, Mihye.
Okay. Thank you very much for introduction. And my name is Mihye Won. I'm at Curtin University School of Education, and I am delighted to give this presentation. And I'm a bit nervous because this is my first time presenting at Immerse Australia. So I don't know your background. So I will try my best to meet your expectation today. Okay, so my today's talk is about collaborative interactive science learning in immersive VR, design for learning. And I am leading Australian Research Council Discovery Project, research project, and with multiple chief investigators and PhD students. David Trigust, Mauro Mosserino, Chin Chong Sai, and Roy Tesker, they are co-chief investigators. And Dewey Ungu and Henry Matov are 2 excellent PhD students. They are joining us today. Okay, so before I go into this research project, I think it'd be good to introduce myself in terms of why I started this project on immersive virtual reality. Okay, so my PhD study was done at University of Illinois Urbana-Champaign, and that is really famous site for computer scientists in the US, because it has one of the National Center for Supercomputing Applications. And in College of Education, we had a lot of collaborative research projects with computer scientists, engineers, and everyone like that. So I was involved in AI projects and bioinformatics projects for education applications. And we had CAVE, like projection of screen on multiple sides of the wall to give immersive feeling into it. And I was interested in doing education technology project like that, but I thought it is just too way ahead of the time. So I thought it is not going to work for educational applications that can be applied to school settings or university settings. So I said, no, I'm not going to do it. And I just went back to educational theories and school research. So when I went to Curtin, I was involved in more of traditional science education research and was happy doing that. And one day I went to Hub for Immersive Visualization e-Research Hive and met Andrew there. And my journey with immersive virtual reality started then. When I went to the Hive, I saw some possibility how we can adopt this immersive virtual reality. I'm going to call it IVR from now on. Not many applications were available then, but we thought if we develop our own program and test it, it is possible to have great impact on science education. So I gathered a research team and started researching in 2017. And from then till now, we are continuously developing IVR programs and testing with students. Okay, so when we apply IVR for learning, I had several questions to ask. One, what can we do better with this technology? We don't want to do this IVR development as a poor second alternative of what is already available. Some people say, why don't you do a virtual lab with IVR? But if you went into a science lab, you have the feeling of the glassware tinkling and seeing the chemicals changing the colors and things. You cannot replace that with IVR. So I did not want to have IVR program that is not really excellent and giving a new experience to students. So that question always came to me, what can we do better with this new technology? And the second one was, what educational problems do we want to address with this technology, and why do we believe this can really benefit addressing that issue? So we just wanted to go beyond that novelty effect of IVR. And in many educational technology studies, people tend to use the technology to present information. It's more of one-way passive information giving. But in education, we said that it's not really effective for learning. So we wanted to really think about what teaching approach and learning approach we are adopting in our IVR applications. So those three questions are really important things. So we investigated what is available out there and how we can use it. So what IVR does well for learning, research studies has found that it really gives new environment, and people can be really immersed in that new virtual environment. If you are adopting 3D visualization and immersive action well, people can be really into the learning task. So some examples can be done. You can assume someone else's body and experience someone else's life in immersive VR. You are not you anymore, you are becoming someone else. And not other media can do that. So it is really a powerful experience that IVR can give. Another one is if you are new to the job and the job itself is really dangerous, you do not want to risk your life getting the training. So IVR can do dangerous job training as a pre-training of your job. And something impractical, impossible such as going to the moon or going to the Mars, so exploring faraway places. So it could give a secondhand experience of field trip to exotic places like that. So if we apply these impossible, dangerous, impractical things in IVR for chemistry education, what can we do? So in chemistry education, we often think about 3D visualization as a key aspect for students to understand. Molecules and molecular interactions are not really visible, and it is of micro scale. So you cannot use microscope to look at molecules and their interactions. But that understanding or visualization of molecular interaction is so fundamental in chemistry learning. But students find it really difficult to do that. So oftentimes we use this ball and stick model to give a second-hand experience of what molecule would look like and how they would behave. But this can be successful in simple models. But if you have really complex models like molecules and enzyme reactions or really big crystal structure, you cannot do that with this physical ball and stick model. And even computer simulation or computer visualization program doesn't give the depth perception. So it is really challenging to visualize the 3D structure of it. So maybe we can use IVR to give that 3D visualization feel of molecules and molecular interactions. And the second thing we thought IVR can benefit for chemistry learning was interactivity. If we are using computer simulations, to turn the molecules around, we have to press Alt key, Shift key, and left arrow, or Shift key and Control key and right hand arrow. So it is not really intuitive to turn molecules around, but we can do that with IVR. You can really grab the molecules and turn it around, and you can switch your body positions to view it from different angle. For example, this is one of the applications we developed. And if you can watch, if you can handle that a bit of dizziness because of the quick turn of the molecules, I will show it to you. Come on. Okay, so can you imagine what it is like in IVR? Students can see from multiple angles, zooming in and out, and changing the position to have a 3D feel of it. And they can touch it, manipulate it, rotate it. And another one of the IVR can do is that it could give an excitement. It could be a novelty thing, but it could give a departure from their normal daily life and experience something quite new and exciting. But at the same time, we do not want to overburden their sensory field to just make them dizzy. So we want to give them something exciting with the new scene of the snowy field, snow falling into them. But at the same time, we want to give them the focus of learning. So simple background when they are in actual learning activity. So this molecule, simple background is there, and they can focus their attention to the molecules. And we did not really give too much burden to CPU and GPU, so that students can enjoy the maximum refresh rate with the really clear image while they are manipulating it. So what kind of education problems do we want to address in IVR? We know students process information piece by piece, and they do not really connect different pieces of information to have really scientific understanding. So we really wanted to use this IVR for students to build comprehensive understanding, starting from complex things and going backward to simple molecules, simple understanding. But now the designer side was that complex thing, starting from there to the bottom of the simple one, but students would go through the experience from simple to the complex. So they would start with 2 simple water molecules and arrange the water molecules to find the angle and distance for optimal bonding. And then based on that, they will build molecular structure with 5 water molecules, and then 10, 15, 20. And then later they can create water molecule structure like with 150 water molecules. So it is gradual progression from simple to complex, but they can integrate the information they already have and apply it to solve the problem later on. And we wanted them to have plenty of time to discuss and justify their answers. So we give some kind of instruction there. We ask them to predict what will happen and explain why they think that way. And then they can manipulate the water molecules to actually see if their prediction was correct. And if not, why not, right? So we gave them explicit prompt for predict, explain, and do, and compare and reflect. And we thought that many IVR applications and many education programs tend to rely on computer and person interaction, not person-to-person interaction, but we know students' peer interaction could be quite powerful in helping students build better scientific understanding. So we wanted to give students opportunity to collaborate and construct knowledge together. So we had 2 students sharing the same physical and virtual space, interacting in the virtual space together, so they can share what they're seeing, what they're thinking. It's quite neat, and I don't think many people try this thing. So in actual situation, it looks like this. We had a virtual studio, IVR studio there, and we had the lighthouse set up at the 4 corners of the room. And students had the wireless headset, and they can move around. They can see each other, not completely, but they can see the headset and their hands. Okay. Okay, so we developed so far 3 applications. One is snowflake ice crystals. And second one was about sweet taste receptor that is based on stereochemistry. And third one is enzyme substrate reaction. It is more complex chemical reaction, but we developed 3 to build from the first one to second one to third one. And if you wish to have watched some of the features of the program, please type in Immersive Chemistry VR in YouTube channel. We uploaded about 6 or 7 program videos, okay, so that you can see some of the highlights of the program features. Okay, so let me quickly give you some description of the program. The Water Snowflake program introduces us into winter wonderland, and there will be some background music to give the feel that students are now moved to virtual environment. And then they will make the connection of 2 water molecules to make hydrogen bonding. And then they will make 5 water molecules connected together to have a tetrahedral structure. And then based on that, they will make a layer of ice. And then they will connect multiple layers of ice. And then compare the layers of ice with the snowflake itself. And they're applying what they learned, discovered, to explain why snowflakes has that particular shape. Another example is enzyme reaction. They will first construct a molecule of the substrate and then see the electron density of the substrate. And then they will explore the protein. They can zoom in, zoom out, and change the representation from electron cloud shape to more of this ribbon shape. And then later they can place the substrate into the enzyme so the reaction can happen, right? And then they will see how enzyme reaction happens inside the enzyme chamber. Okay, so I will quickly give you some background of the hardware and software development there. We use HTC Vive Pro I headsets with wireless adapter. The main reason was the Vive was the only option available for multiplayer networking in the same physical space. So we chose that. And then we later upgraded to Pro because of the resolution. And then we were using cables from the headset to the computer, but it was limiting students' movement. So we changed to wireless adapter setting. And we use the two desktops. It is not really high-end desktop because we wanted other people to use this application more readily. But we use the wired network connection for stability of network and minimize network latency. Because they were sharing the same physical space, they could feel the movement of the partner. So if the synchronization is a bit off, they feel they might collide to each other or they could hit or something like that. So we really wanted to reduce the network latency between two players. And software is developed with Unity 2019 long-term service version. And we, as I mentioned earlier, we include simple elements to reduce the CPU usage and thus reducing the motion sickness of the students. And simple user interface is adopted because not many people are familiar with IVR interface. So mostly we use the trigger button of the wand to grab and release or move around. And the simple interface was to submit, go back, and reset. So the students can retry and redo and learn from their mistakes. Okay, so data collection. We collected data from over 130 first and second year chemistry students in later part of 2020 and earlier part of 2021. Most of them didn't have experience with IVR, but some did have some experience with IVR, as like handful of students had their own headsets at home. The VR studio was not small, not big, so 3.5 meter by 5.5 meter with the adjacent interview room available. And we had a pre-interview to orient students, give some interview questions about their prior experience, their background knowledge in chemistry, and explain the whole experiment to them. And the VR session lasted from 35 to 1 hour, but usually it was about 45 minutes or so. And after that, we had a post-interview to reflect on their experience. We collected lots of data in terms of videos. We had 2 videos set up from the above to look at students' movement, and we had audio, and we captured what they are seeing with the eye and location tracking data. and we asked them to draw their chemistry understanding before and afterward. And I think most of debugging, most of the programming time was spent for multiplayer synchronization. Students behaved in a different way than we anticipated. So if there was some kind of disruption in synchronization, we quickly changed and updated the program so that the next batch of the students can go through the program without much glitch. So, okay, so this is the combined video. One is the upper hand side is the room video, and the bottom two videos are screen captures. And we can follow how students are seeing, what students are seeing. And if you look closely, you will see orange cross. That is the focus point of their eyes. How am I doing with the time? Okay. So when we asked them about what their experience was, they often talked about 3D visualization as the most stunning aspect of IVR, of course. And their drawings, conceptual drawings, show they improved their understanding of chemistry. And they realized, they thought that those visualization, 3D visualization of molecules and molecular interactions were real. And I'll just read the quote here. When I accidentally zoomed in too fast, I thought the electron cloud would hit my face, I was like, whoo, moving back. So they really felt that the electron cloud, the visualization in VR was real thing. And some students that thought that they felt claustrophobic when they zoomed in too fast. So they were enveloped by the electron cloud inside VR. So they felt it is really real thing. And one thing that clicked with me was that the big structure of the 3D crystal is not flat layer. I could really see that was optimizing the distance and angle between the regions. It's just really good way of registering it into my head. So students thought that the 3D visualization really helped them really realize what they learned in chemistry lectures and register in their mind. Yeah, it is not something that you can really describe with words. Once you see in VR, you just get a new perspective. I pretty much imagine an enzyme would be like a dot, going like this, breaking it up, but it is so different. So it is really new insight of molecules and molecular interactions. And they said what we learned in class was misleading a bit because it relies on your own perceptions of what it could be rather than actually showing what it is like. And interactivity, students really enjoyed the easy manipulation of molecules and explored the virtual world. They went back and forth and seeing many things. We can actually move the molecules with our hands. And I thought it was really cool. It was nice to see the structure and to be able to move them, rotate them, and redo it. Have the pseudo tangibility of something that is normal in the domain of textbooks and YouTube. And it was really nice. And students talked about the abstract concept they learned in chemistry lectures became something really concrete. And something really concrete so that they can really handle it. But the distinction between what is real and what is not was a bit blurry because in science, we simplify things to help students learn or help communicate the main ideas, but it is not exactly the same thing. So there is complexity missing in simple representations. So it is a bit tricky to balance what is real and what is not in IVR, especially so than textbooks or 2D screen visualization. And familiarity and prior experience with the IVR interface determined how they interact in VR. For example, if they found the interaction, the action they were doing was not working, some students thought, wow, why it's not working? What are we missing? So they step back and try to adopt a different strategy because they are quite familiar with this kind of problem solving computer programs. So they try different angles and succeeded. But some others were focusing on minute details and feel really frustrated by not being able to succeed. On the other hand, some students were really confident with their answers and they said, the program must be glitchy and we are right, let's move on. So based on their experience, the interaction in VR was vastly different. And most of the students enjoyed this fun, novel, exciting experience in VR. It feels really far away from the normal chemistry class. It is not just physical location of the building, but the way they learn new things or apply their knowledge to solve this problem. It was really different from the way they usually learn in chemistry labs or chemistry lectures. And some students talked about they were actually in the winter wonderland. They felt it is really chilly inside the room, even though it was reasonably temperatured room. So they said, we felt we are like in the cold, like in a different climate. So it was quite interesting. I said usually they spend about 45 minutes or so. But when we asked them, how long do you think you spend time in VR? They said, 20 minutes, 10 minutes. And we told them, you spend about 45 minutes. Oh, I didn't realize I spent that long time. It was so fun and it was so exciting. We were doing things all the time. So they didn't really realize the time they spent in VR. And it was another interesting comment was that I didn't see you guys, so I wasn't distracted or self-conscious. So they were actually in the zone of VR and doing things. And when we asked them to just take off their headsets to come back to the real world, they said, no, I want to stay here. Can I stay here a bit longer? I'm enjoying my experience here. And some students said, can I download this app? Where can I download this app? I want to try it at home because I have the headset. So that was really good feedback from students. But thing is, exploration of virtual or physical space was tightly linked to conceptual and social aspect. And we didn't anticipate every aspect of it. I will discuss it in the later part of the slide. But not just enjoying is our goal in chemistry learning IVR. So we really wanted to see how students are actually learning and exploring the concepts and applying it from the experience. I talked about the social aspect as social construction of knowledge as our learning and teaching approach in IVR. And students most frequently talk about this as really exciting thing, enjoyable thing. Partner there in VR really help them immerse themselves in learning tasks. You feel like a little bit dorky with the headset on, swinging around wildly, but someone else is there with you and you are both doing it, you get into it more. So they felt it's not them alone. They are doing it with others and they cannot really see other researchers inside the room. So they felt really left alone to do whatever they feel like it. And they were really bouncing ideas off of each other. And they said, oh, we can just talk to each other and then we can explain it. And then when my partner wasn't really seeing what I was seeing, I could just ask him or her to come over to my side and show what I'm talking about. And it is quite easy, right? You can just tell each other like, now come look at it from here, from this angle. Group dynamics in and out of IVR was quite interesting. Some groups sustained their group interactions outside VR, inside VR, but some groups changed their group dynamics in VR. I'll talk about it in later slide. Some students were not really used to verbalizing their thoughts out loud. So we had to have lots of prompts for them to predict, observe, elaborate ideas. In VR, they were quite quick to grab things and move things and see what happens rather than thinking about it and do it later. And multiplayer networking in Avatar was really tricky thing. If we had the students in the separate physical space, not really feeling each other, I think multiplayer networking could have been easier because you do not feel other person standing next to you. You can just talk to the other person, but we wanted to have them in one classroom, one room, because that is what classroom would be like if we are going to adopt IVR in future in school setting. So because of that insistence of keeping students in one room, there were lots of more complex issues. So spatial exploration was really interesting thing. We collected data of where students were in the room. And group A and group B, those two groups of students explore the virtual space quite differently. This is a heat map. The left-hand corner, graph, the orange is representing one person, Craig, and blue represent another person, Aiden. And the red circle are water molecules, the center of their attention. So when they are doing this activity, they didn't move a lot. They were looking at the water molecules from their own position, right? And group B, Pascal and Keenan, they were doing the same activity, but they were moving a lot, quite a lot. As you can see, the blue dot moved to the orange dot area, and orange dot move over to blue area. So that means students swap their positions to see what the partner was seeing. And they moved around a lot. But the difference between group A and group B was that group A had a tutor interacting with the students. As a teacher, we just cannot help ourselves to help students see what we want them to see. So we were guiding students to see some of the features in VR. Of course, they cannot see the researcher because they had the headset, but as a researcher, we could see where they were and what they were seeing with the monitor. So we were guiding students to explore the IVR more effectively, conceptually. But because we were guiding them, they felt they were quite limited they felt they couldn't really explore the whole space freely. So they stayed in their own spot and focusing on the conceptual thing and getting the details right. On the other hand, group B, we didn't really intervene at all. So they could really explore the virtual space more freely. And it was their partner they could rely on. So they had more rich conceptual discussions. The Craig and Aidan's group, they mainly interacted with the tutor, and conceptual talk was mostly done with the tutor. About 58% of the total talk was conceptual talk, and other thing was very procedural and just agreeing to each other and staying at the same position, focusing on the details, getting things right. On the other hand, the Keenan and Pascal group, they were quite into bouncing ideas off of each other, and collaborative conceptual talk was about 72% of the total talk. And they changed positions repeatedly to reach a consensus. That is the initial task, but when they moved the more complex task, their behavior changed a lot. So this square in the middle is a big isolated structure. So they can go inside the isolated structure, coming out and see how water molecules are connected to each other. Okay, so different from two water molecule interaction, they were moving a lot more and they were changing positions quite a lot. Still, Craig interacted with the tutor more, but they were inside or outside the lattice to explore the concept. And Keenan and Pascal group, their collaborative conceptual talk increased from 72% to 87%, even more. So they could move in and out and back and forth to explore the structure more extensively. And they also talked about why and how questions more in this task. Maybe because they now were more used to the task and interface. Maybe because the task itself was more complex, they had to really think a bit more. So we do not know what was the main issue, but students were able to really use this complex task to develop their understanding and build knowledge constructively with their partner. Okay. But when we talk about complex tasks with time, encouraged why and how conceptual questions more, we have to be really careful where students are starting from. Because they were chemistry students, we assume that they have some basic understanding of hydrogen bond and molecular structure and things like that. But some students did not have the understanding we were anticipating. So it was a bit difficult for them to build understanding from that level to the level we were aiming for. And group dynamics, some students were quite domineering and they didn't really give the partner a chance to explore ideas and build ideas collaboratively. So we had to do some management issue there, and we used the pre-interview to set the tone and give communicate our expectations to students to make the IVR activity more successful. Okay, so implications for educational IVR research. For design and development, I think storyboarding needs to go beyond the novelty effect. People often think about, is IVR is new, let's try it. But we need to go beyond the novelty effect and see what problem we actually want to address in IVR. And collaborative, interactive, and constructive IVR may bring a lot of technical challenges and demand flexibility, but at the same time, it will bring great joy, enjoyment to students and great educational benefit as well. So in terms of evaluation, we need to really think about how students are exploring IVR experience, physically, physical space, and conceptually and socially. Once we do examine students' exploration in 3 different areas, we can better understand what experience students have and how we can improve IVR application development. Okay, thank you.
Thank you, Mihye. Appreciate your presentation. I must say that, actually, if you want to stop sharing, we'll get everyone's pictures on screen. If at this point you'd like to show your faces and do a little bit more of an in-person experience to allow Mihye to see your smiling faces. If you do have a question, just use the, where is it? The reactions icon on the bottom row of your Zoom interface. And from there, you can just put up your hand, raise your hand. And yeah, so if you've got a question, just raise your hand and we'll allow you to switch your microphone. I didn't mention at the start, but my day job is to manage the Hive visualization facility at Curtin University. And Mihye and I first met in, I think it was 2017. And it's been amazing to see the project progress over the many years, from a small initial student project right through to an ARC discovery grant. So it's really good, and it's also good to see some of the results happening now. If no one has a question, I'm going to ask one. I'm going to sneak one in. What have been some of the more unexpected reactions of when users have experienced your VR experience?
Unexpected reactions. No, we anticipated every reaction. We initially, at least very first study, we didn't expect that positive response from students. We thought students would politely say, yes, we enjoyed it, thank you. But some students' reaction was extremely positive. That was amazing. It was really wonderful experience. That kind of reaction we didn't anticipate, but we did get that reaction from students. And in the later part, I talked about the students' prior experience determining their enjoyment, their interaction in VR. Some students felt really frustrated because they want to get everything exactly perfectly right. And if they do not succeed, they felt really frustrated. They spent a really long time, amazingly long time, to get things right instead of moving to the next one and trying different strategies. So we didn't really anticipate that. It was a bit really eye-opening moment. We thought we were prepared enough to get diverse reactions on students' interaction in VR as we develop more and more experience with IVR user testing. But some students' reaction was a bit, in my opinion, a bit different from how I expected it. So we really had to think and take a different route in terms of guiding students' interactions there. And so that's why we included lots of prompt. And if it doesn't succeed, it's okay, and try a different way. So we added a bit more guidance in the program. Yeah.
Thank you, Mihye. We have a question from Steve Pretzel. We'll make sure you get your microphone. There we go.
I think I'm on. Thanks for the presentation. It looks like a really interesting experiment. You've focused a lot on the experiential outcomes of it and the observations. Did you have a look at the impact on the learning outcomes? Was it possible to get an understanding of the depth of understanding of the content from the IVR?
Right. So I didn't really go into chemistry side because I wasn't really sure how people are familiar with the chemistry concept there. The most common understanding of water molecule is that they know how water molecule would shape like. So one oxygen atom and two hydrogen atom, and they had a bent shape, but that bent shape was very much in a flat surface. So they knew some of the lone pairs were there in oxygen, but it was in the flat surface. It is 2D structure basically instead of 3D. And because of that 2D structure understanding, they couldn't really think about how other water molecules would come in and make hydrogen bond. So hydrogen bond was forming in a different angle than it would in real life. So when we show that in VR, they say, aha, I didn't think of this before. And another one was enzyme. They talk about enzyme reaction. It is shape dependent. But as I showed in one of the quotes, since the enzyme is like one dot and breaking apart, it's lock and key, simple lock and key structure. Instead, they inside VR, they realize there are tons of amino acids inside, and the enzyme reaction chamber is really complicated, and how the enzyme is organized is quite intricate balance to make the reaction perfect. So when they came out to real life, when we asked them to draw the diagram of water molecules making hydrogen bond, they said, I cannot really show 3D structure in this piece of paper. You have to have this hand gesture coming in and out. And for protein reaction, they said, I didn't really realize that complexity and the simplicity in enzyme reaction. So they were able to explain things, but when we asked them to describe the reaction mechanisms of the enzyme, they couldn't really say, I don't remember, right? So because it is way beyond the first year students' understanding level, they had some understanding. They built some understanding of the basic aspect of it and how they can apply the basic understanding to the enzyme reaction, but they cannot really recall the exact name of the amino acids and how the reaction mechanism happened. So that is a bit way beyond the understanding, but we did check what they learned and what they did not learn. Yeah. Thank you.
Thanks, Mihye. If anyone's got any other questions, feel free to raise your hand on the Zoom interface. I'd also like to acknowledge a few people on this call. I just noticed that Adam Matthewson has joined us. Adam was the first project student to work on the project through the Hive Summer Internship Scheme. So
Hi,
if you're
Adam.
able to turn on your camera and say hello. There's also Henry and Dewey, who are PhD students on the current project with Mihye, and you saw their photographs in some of the slides. So thank you to Adam, Henry and Dewey for joining us this evening. Hi, Dewey. Is there any other questions? I think Robert had some in the background. Robert's in the Immerse Australia boardroom at the moment. I'll get a question from Ivan as well. Or maybe I'll just read it out. Ivan, did you want to read your own question?
Yeah, sure. All right. Thank you for the interesting project. Can everyone hear me?
Yes.
Oh yeah, cool. Okay. But I would like to ask two questions mainly. The first one, I know this IVR is still very new, very novel, still at a very early stage. But how practical do you think it is to run the IVR classes in an institution since a headset is required for every single student? And in your project, only use 2 headsets, and so only 2 students were allowed in 1 classroom.
Good question.
Yeah.
Right. We chose this Vive Pro partly because it can be extended to 16 people. But in our setting, we just had 2 students because we do not really have that big room to host 16 students in that room, and we didn't have the 16 headsets.
That's even too many for the Hive.
Right. But we contacted the chemistry instructors. So some later part of this user trial was linked to a particular class. It was part of the lab aspect to it. So instead of going to the lab, they were coming to our IVR studio to conduct this as a learning experience. So if you have that kind of link up to existing chemistry unit, you can run it. And of course, in a school setting, you have about 30 students in one class, and we cannot have 30 students all at once to experience the same thing. And if we think this can be applied to school right away, that would be lying. But I am thinking of new development of IVR headsets, and we can use this technology, this knowledge, to apply and develop newer one to host 30 students. Andrew has been saying all along, we need to go Oculus Quest 2 and other versions so that many students can experience at the same time. The limitation of Oculus Quest 2 is that it is not really allowing multiplayer networking at the same time. So it is more individual play in one room instead of multiple students seeing each other, interacting with each other, right? But as an educational researcher, I believe it is really important to encourage that kind of collaborative interaction in learning. So that is why we insisted on using this technology. But if HTC or Facebook upgrade their technology to involve more students and networking to see each other and interacting with each other, that could be fantastic. Does it answer your question?
Yes, thank you. I do have another question. So during the experiment, did the students experience any system glitch or any technical issues while you run the program? Is there any issues with it?
Of course. I talked about the synchronization issue because the Unity dropped the unit in 2019, and before they dropped support of unit, it was tricky. But after they dropped the support of the unit, it was even more trickier. But we were using some of the documentation other users used to troubleshoot the synchronization issue. But it was tricky because some Unity errors could accumulate, we do not know, and then crash the networking system. So it was really time consuming to troubleshoot networking synchronization issue. And that was one thing. But once we fixed the networking issue, it was more smooth. Another main issue was the wireless headset adapter. The battery sometimes unexpectedly just drop out. So we had to do something, and we had to buy additional batteries to be safe, right? So if I say we had no issue whatsoever, that would be really lying. But we were able to manage and run the session partly because Dewey and Henry were there running the session and checking everything. The battery is fully charged and the cable is fully connected and everything. So we were there to see how students were progressing. And the programmer was really quick to fix the bugs, fix the synchronization issues, and come back and supply the updated version the next day.
Well, thank you, Mihye. I think at this point we will stop the official proceedings. We will still allow questions remaining a little bit afterwards, but just for those who need to leave at, well, 8:02, we'll finish now. And I'd like, of course, to thank Associate Professor Mihye Won for a presentation tonight. So please, everyone, put your hands together.
Thank you.
I'd also like to thank the people behind the scenes. So Olivia, Phoenix, and Robert, making it all work. We had a few little hiccups, but we got there, fortunately. Our next Immerse Australia event is in just roughly 2 weeks' time at the XRWA conference and exhibition, which is at the Perth Cultural Centre, Friday the 17th of September until Sunday the 19th of September. There are a series of panels, particularly on the Friday, which many of the Immerse Australia committee will be participating on. So I'd encourage you to visit xrwa.com.au and see those events, as well as, of course, visiting immerseaustralia.org to see what the events are and activities are for Immerse Australia, and also, of course, join. So thank you, everyone. For those who want to remain and ask some questions, please do. But otherwise, thank you. We'll see you.